Okay, welcome back. So, let's continue where we left off. I introduced you to myself and the IB-DP chemistry program. Let's get into a little bit more actual course content now. So, you can see my slide here, important tools before starting chemistry. Now, I know a lot of my students come to the class thinking they're going to immediately learn about explosions and fire and lightning and all the cool stuff that comes with science. But look at me for a minute, guys. Science and math communication, I think, really needs to be the first thing that we learn here. It's so important. As I mentioned, we're in high school now, and we need to be able to predict and plan and analyze reactions, okay? Not just describe what we see or what we feel with our five senses. So that's going to come down to math and science communication. Now, I am a little bit hesitant to start with this as the very first thing, because I think it scares some people off. It's not super exciting. And I will say, I think probably about 25% of any students who join my class, my school has a trial period, and 25% of those kids decide not to do chemistry. And I feel like the fact that I start with this might have something to do with that. But on the other hand, if you're not able to do this and you give up, it's probably better that you leave anyway and try something else. Let me put it that way. These things are so important for you to understand and do your assignments and exams properly. So what am I talking about? Math and science communication. Significant figures. Maybe you've heard of that before. Scientific notation. SI units and other units. Unit conversions and dimensional analysis. So important. Subscripts and superscripts. Uncertainties. And finally, proportionality. Okay, so before we even do any science, we need to talk about these things. These things are mostly mathematics. You can consider units as kind of a property of our universe. We have different ways of measuring things like length or mass or time. It's not exactly pure math. That's why I'm calling this section Math and Science Communication. But let's go through some of these things. Significant figures, or sig figs for short, or SF. So, you have to ask yourself the question, how many digits do we use to record a measurement if we go measure the length of something with a ruler or the volume of something with a flask or whatever? Or how many digits do we use when we report the result of a calculation? So maybe you want to measure the speed of something. You go and you measure the distance it travels, and you measure the time it takes to travel that distance. Then you're going to put those things together in an equation as a ratio. You'll get distance divided by time, and out comes a speed in meters per second. But you've got to think about how many digits you report for that speed, and it's going to depend on the digits in your measurements for distance and time. Alright, so this idea comes from our confidence in the measurements. So the idea is you can write more digits as you are more confident with that degree of precision in your measurement. So significant figures are super important for scientific communication, safety, and certainty. Okay, so if I go to publish my results to the world, other people who read my results want to know exactly how careful and how precise and how sure I am of my results. For safety, maybe we're talking about like the level of toxins in food, for example, like how much lead is in your food. You've got to know exactly how much to a very specific precise measurement, because we have regulations and previous examples throughout history that says there is a precise, or at least range of toxin in our food that's not allowed. So when we scientists go to measure such things, we also need to be as precise or more. And for certainty, sometimes you want to be very certain. I mean, this is related to the previous two, but for example, I used to work in a laboratory with a glove box. We had air-sensitive compounds, and these things would react with O2 or with H2O in the air, and they had to be dealt with under inert atmospheres of nitrogen or argon. We'd put it in this box that's filled with this gas, but I mean, what level of gas purity is good enough? 95? Is that good enough? No. 99? Is that good enough? No. 99.9? Getting there. 99.99? Some of these compounds are extremely sensitive, and you need to be very precise about, the degree to which you're reporting amounts of certain things to actually get work done a lot of times in the real world. So significant figures carry through calculations. As I mentioned, you'll have them when you make measurements, but you'll also have them when you do mathematical operations on those measurements and get a final result of some calculation. So these things are easy to forget. My students forget them all the time. Anytime we go to the lab, I try to remind them, but the reports come back, and after, line 1 out of 10 calculations that they're supposed to do, they just disappear. They can really increase the amount of time that something takes. You'll realize that as you start to try to use them, but it's really important. IB really cares about this. So try to learn how to use them, and don't forget to use them. So the general rule, there's a whole explanation you can give of what significant figures are and the rules behind them, but I think I've concentrated the rules down to this phrase. So ignore leading zeros. That means zeros before a digit which is not 0. For example, 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Zeros before that are insignificant. Don't really worry about them. And ending zeros with no decimal are insignificant. So this would be something like 1,000. The 3 zeros in 1,000 are insignificant. They don't tell you about the precision of a measurement that was made from someone who reports the number 1,000. Okay, so if you think about this, the inverse of this is what's significant then. So zeros which are not leading, or which are a part of a number which has a decimal point, are significant. So that's how to judge whether something is significant or not in a nutshell. But you need to practice and see whether you understand this and whether you can get it correct for yourself. So what about when we go to take measurements? You kind of need to split your instruments into two types. There's digital instruments, which are like computerized and computer-based, and then there's analog instruments, which are more line-based, and you decide what the number is based off your own vision. So I've got some images here. I do use AI like Google Gemini to generate some of these. So I try to make that clear whenever I do that. I'm not totally against AI. I think it can be a helpful teaching tool, but don't rely on it too much if you don't have to. So digital instrument here, we have an analytical balance, it looks like. And if you look closely there, it says 100.00 grams. So when you go to record this in your notebook, what are you going to write? You're going to write 100 grams, or 100.00, or 100.000000. Well, this one I think should be fairly obvious, and it is a rule that you can basically write the exact number that a digital instrument spits out on its display. Okay, so you can write this block is 100.00 grams. And if we follow the rules of significant figures that I had on the previous slide, there's no explicit leading zeros here, so we don't consider anything before the 1. There is a decimal point though, so any zeros in this number are significant. And that leaves us with 5 decimal points. Sorry, 5 significant figures, 2 decimal points after the decimal. But the 1 and all 4 of those zeros are significant because we have that decimal place. And if you think about it, it kind of makes sense. This instrument's trying to tell us that it's confident about all 5 of these numbers as it displays them. Alright, so I would choose the middle here. Let's see if I can circle that. This very often appears on multiple choice type questions in paper 1 as well. Anyway, what about analog instrument? This is where things get much more complicated. So I have a graduated cylinder here, something that's commonly used to sort of accurately measure volumes, although there are better instruments. So we've got a 50 milliliter graduated cylinder, and it's filled up with water. And please ignore the fact that there's 11 lines between 40 and 50. Again, this was made with AI, so there's some wonky bits, but if we just consider that 4 lines above the 40 line, 1, 2, 3, 4, is basically where we find our water. But do we write this as 44 milliliters, 44.0, 45.0? Because the little dip there at the edge does go up to 45. So I'm curious what you think. But here's what I would say. Okay, there's a rule about measuring liquids in containers like this. Maybe it's the first time you've heard it, but this little curve is called the meniscus. And you need to take your volume measurement from the bottom of this meniscus. That means we're not going to choose 45, we're going to choose 44. And are we going to choose 44.0 or 44? Well, you might say the lines only go by milliliters, so we should choose the top one. But the rule for this is, in IB anyway, that analog instruments, you can actually get an extra significant figure out of an analog instrument beyond what these lines show you. Okay, so you can actually get 3 significant figures from this instrument. It's graded milliliter by milliliter, but when you write this measurement in your notebook, you can write 44.0. And this is going to go along with something called uncertainties later on, but for now, let's just consider, we'll label this as 44.0 milliliters. Alright, so there are practice websites that you can use for this. Maybe we'll go check out one of these right now. Hold on just a moment. Alright, I think this is where my link sent me. khanacademy.org/math blah 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 into significant figures. So maybe we can do some little quizzes here, practice questions. How many significant figures does 0.066772800 have? Alright, so the first part of the rule, leading zeros are never significant, so we ignore those first 2 zeros. But there are 3 zeros at the end of this number, beyond the decimal place. Those will be significant. So if we count how many there are here, 1, 2, 3 zeros, and then 1, 2, 3, 4, 5, 6 non-zero digits. So 6 plus 3 will give us 9. Let's see if I can input a 9 here. Got it. Alright, can we move on? Next question, let's try another. How many significant figures does this number have? So this number doesn't have any zeros, so basically everything here will be significant. 1, 2, 3, 4, 5, 6. Got it? It would be pretty embarrassing if I got any of these wrong, but once you understand these rules, you kind of really do understand them, and you don't make mistakes other than forgetting to even think about it. Okay, so how many significant figures does 0.0919 have? So leading zeros, never significant. Then we have 3 other digits. This will have 3 as well. 3 significant figures. All right, that's enough. If you want to go beyond that, feel free to use my link or just go to this website or any other website. Practice your significant figures. All right, let's go back. So I do want to consider significant figures in calculations as well. So there are rules for how to bring your significant figures from a measurement through a calculation. So the first rule, for an operation involving multiplication or division, your computed result, your answer, should be expressed with the same number of significant figures as the input with the lowest number of significant figures. And this should really make sense to you because you can't gain extra precision by putting a bunch of numbers through a formula, right? A chain is broken by its weakest link. That's one way to think about this. So whatever your least precise measurement is that has the least number of significant figures determines the output of a multiplication or division operation answer. So what about addition and subtraction? In this case, your computed result should be expressed with the same number of decimal places as the input with the lowest number of decimal places. So it's phrased the same way, it's just instead of significant figures, you think about decimal places. Alright, so if I have 1.0 plus 2, 1.0 has 2 sig figs, 2 has 1 sig fig. So when I write my answer, I cannot write 3.0, okay? The decimal place gets lost because I'm adding it to the number 2, which has no decimal place. It only has one, number on the left of a decimal. So if you try to add together numbers where one of them has less decimal places, then your decimal places get cut or lost through that calculation. All right, maybe we'll do some practice on calculations soon, but I also want to include scientific notation in this discussion. Sorry, I'm realizing some of these words are hard to read on this background with the white lines and things, but just bear with me. So scientific notation is a way to write numbers, and it's often used for large and small numbers, but it can be used for basically any number. And it takes this form, a number times 10 to the power of, to the exponent of, some other number. Now, linking this to significant figures, the first number there, number in brackets on the left, that contains your sig figs. So it contains all the information about the precision of the measurement. The second number describes the size of your number, the order, the power of 10, and also how to move your decimal place if you want to return to your regular notation. So an important point about writing scientific notation properly is that your decimal point always needs to be after the first digit, all right? So if I have the number example here, 850,000, I need to write that as 8.5 times 10 to the 5. Okay, I can't write 85 times 10 to the 4. That's not in complete scientific notation yet. You need a number and then a decimal, then however many other significant figures you have, times 10 to the power of some number. Okay, the decimal is always after the first digit. So let's see some examples here. Oh, there, it's much easier to see. I should have pressed on the screen for a second there. This is easier to read. All right, so some examples. Write 635 in scientific notation. So you need to move a decimal, which, although was not originally written, you can imagine there is a decimal place just after the 5 there. But we need to move that 2 spaces to the left in order to get 1 digit, and then a decimal, and then 3-5. That means we need to multiply this by 10 to the power of 2 in the scientific notation. And then if you want to go backwards, the 10 to the power of 2 says you'll move the decimal 2 digits to the right. If you do that, you'll get back to 635. All right, another example, write 0.00004304 in scientific notation. So we need a digit, then a decimal, then the rest of our significant figures. So we need 4.304. To do that, we need to move the decimal on the original number on the left to the right 5 places. So in the previous question, we moved the decimal place to the left. We ended up with a positive power of 10. But here, we're moving the decimal place to the right to indicate a number that's less than 1. We need to multiply by 10 to the power of minus 5 then, when we go in this direction for small numbers. All right, and then if you want to go back to your original number, you can take times 10 to the minus 5 and then move this decimal place 5 spaces to the left. You'll get back to 0.00004304. And then last, write 300 with 2 sig figs. This is a really important tool as well. So oftentimes you'll have a measurement or a result that's 300. Your calculator just spits out 300, but you know that you're supposed to have 2 significant figs in this number. And the way that this is written, 300, how many significant figures does it have? Only 1. There are ending zeros with no decimal place indicated. So those zeros are insignificant. That means only the 3 is significant. But if your number is supposed to have 2 significant figures, you can write this in scientific notation. 3.0 times 10 to the 2 is mathematically equivalent to 300, but it has 2 significant figures. Remember, significant figures are indicated in the left side of a scientific notation number. If you just wrote 300 and then a decimal place after the second 0, now your number has 3 significant figures, and that might be beyond what you are comfortable or confident in expressing, and it might be the wrong answer on a test to have 3 significant figures. So writing it as 3.0 times 10 to the 2 is a way to write the number 300 with only 2 significant figures. Very useful tool. All right. Let me just see if we can go back. Is there any other practice websites? Yeah, chemquiz.net. Let's try that one and see if we can do a couple questions. I like this website for several different topics, but let's try significant figures. We'll do 5 problems. We'll do sig figs with rounding, multiplication, division, decimal and scientific notation. I don't know, I prefer comma to separate thousands. We'll not include units yet, but you can maybe later if you do this on your own. Fill in the blank. It's probably better to make sure you really understand. Alright, start. I'm writing with a pen here, so it might be difficult for me to write some complex numbers, but let's try. So, what is 3.9 times 10 to the 6 minus 5 times 10 to the 3? So right away, it's kind of a challenge. So you have two different powers of 10, and you're trying to subtract these things. It's really not easy to do. What you want to do is get both of these to be, I think, the same power of 10. So you can either make 5 times 10 to the power of 3 into a 10 to the 6 number, or you can make 3.9 times 10 to the 6 into a power of 3 number. Okay, sorry for a little edit here, but I've decided to just copy those questions onto a piece of paper I have and then switch to my whiteboard screen so I can actually talk and write numbers at the same time. So our first question there was 3.9 times 10 to the 6 minus 5 times 10 to the 3. We want to know what that is with correct notation and significant figures. But we cannot easily subtract two numbers that are different powers of 10. Alright, so 3.9 times 10 to the 6, we can either change that to 5 times 10 to the 3, or we can change 5 times 10 to the 3 to 10 to the power of 6. And since we're doing a subtraction and we want to consider the decimal places, I'm going to keep 3.9 times 10 to the 6 as it is. And then what is this number, 5 times 10 to the 3, as a power of 6? One, two, three. 0.005. All right. You can check if that's true, because what would that be if you turn it back into a regular number? You'd go 6 decimal movements to the right. 1, 2, 3, 4, 5, 6. That would be 5,000. Is that the same as 5 times 10 to the 3? Yes, it is. So we can then apply the rules of decimal places to this. 3.9 times 10 to the 6 minus 0.005 times 10 to the 6. But we need to keep only the lowest number of decimal places. 3.9 times 10 to the 6. The other will essentially be rounded to 0. And that means you end up with just the starting number on the left, which is a weird idea. But we're going to start seeing a lot of things like this. Things often disappear when they become insignificant. And you'll often be asked to prove, like on an exam question, that something is insignificant. And you can use a calculation like this to do that. Alright, so that's, I think, the answer that I'll input for number 1, 3.9 times 10 to the 6. Alright, number 2 was a multiplication. 4.35 times 10 to the 3 times 4.00 times 10 to the 0. Alright, what's anything to the power of 0? I believe that that is 1. If I'm not mistaken. So your math ability and knowledge comes into play a lot of the times here when we're dealing with these exponents. So the answer to this, 10 to the power of 1 is 1. That's going to be multiplied by 4. So we're just going to have 4.00 times 4.35 times 10 to the 3. So 17,400. All right. So that's the number that your calculator spits out, but you need to consider how to write this with the proper number of significant figures. Both of my inputs have 3 significant figures. So my answer here also should have, and it already does, the two ending zeros with no decimal are insignificant, so 1 and 7 and 4. That's fine, but I'd like to write this in scientific notation, so this will be 1.74 times 10 to the 1. 1, 2, 3, 4. Alright, let me square my answers here so I'm just clear on what I'm going to input. Alright, I don't think it's wrong if you don't write this answer in scientific notation, but read the question that you're answering to make sure. Okay. Number 3 then. That was 9.71 times 10 to the power of 2 times, or no, it's just round this to two significant figures. So right now it has three significant figures, 9 and 7 and 1. If we want to round this, we'll take the digit that's farthest to the right and consider, is it 5 or higher? Then we need to round up. If it's lower than 5, we'll round down. 1 is, of course, lower than 5. So we'll round this to 9.7 times 10 to the 2. Now this has two significant figures. Alright, let's go next. Oh, I just realized these numberings are a little off. Yeah, I think this was number 3, this number 4. We skipped number 2. Do number 2 next. So that was 0.6590 times 5,000. So you can just put that into your calculator. $3,295. But you're not done there. You got to consider how many significant figures should this have. How many were in your inputs? The first number had 4. 6590. Don't consider the leading zero significant. The second number has 1. No decimal point given, so all of those ending zeros are insignificant. Only the 5 is significant. That means my answer here can only have one significant figure. That means I need to round everything that's after the 3 down to zeros. So again, 295 is less than 500, so I'm going to round this down to 3,000. And if you want to write that in scientific notation, not 3.0, just 3 times 10 to the 1, 2, 3. Okay, that scientific notation also has one significant figure. Alright, I know some of these are tough, but you should really do this quiz and practice until you can consistently get them right and understand the rules. If you get anything you don't really follow or understand, put it in the comments. I'll take a look at it. Alright, then the last one, number 5, is just a number and asks how many significant figures. Are in this. So the whole times 10 to the 8 doesn't contain significant figures information, so ignore it. Then you have 4, 7, 5, 3, 4. That's 5 digits and 5 significant figures. Alright. So I'm going to go try and put these back into the quiz and hopefully get all the answers correct. If not, that would be embarrassing. Alright, so these are correct. Alright, so you can do similar quizzes like this and set it up for yourself. Let's go back. Okay, this video ended up being way too long, so I'm going to split it into 2 parts. That's all for this part. Hope to see you in the next one.